Well, we're filming this from a remote location in a satellite circling the Earth or circling Starbucks or something. This video is about the motion of satellites that circle the Earth or any planet. Could be the moon, could be the space station, could be a Soyuz capsule, could be a spy satellite. But we're going to talk about the motion of satellites. It's not that hard. So this is section 12.4 in Young and Freedman's University Physics, but you might, if you don't have as cool a textbook as this one, it might cover this sort of thing. Maybe it does. Well, first, in this section, we want to talk about what kind of velocity does a satellite need to have in order to stay in orbit. And here, let's just assume that we have a perfect circular orbit like I have in the space capsule that I'm in right now. So, we can take some things that we found in earlier parts of the book, or your book. So on the right here we have g(m), mass of the Earth, times the mass of the thing that's spinning. So I'm what, 120 pounds plus this capsule. So the gravitational constant times the mass of the Earth times the mass of this capsule divided by the radius squared from the center of the Earth. So whatever height the satellite is, the radius from the center of the Earth to that height squared. Now, so that's something that we've been talking about a lot. That's basically Newton's law of universal gravitation on the right side. How did I get the left side? Well, you might remember from an earlier chapter that v squared over r is the acceleration needed to keep a circle spinning. If a circle is spinning, and you can go and see an earlier video to see why this is the case, but if you have something spinning in a circle, perfect circle, then the acceleration inward at any point is going to be the velocity squared divided by r. So by multiplying that by the mass, F equals ma, we've multiplied the acceleration times the mass of the thing accelerating. So now we can set these two equations together. On the right, we have Newton's law of universal gravitation, and on the left, we have something we discovered when we were talking about motion in a circular, perfect circular motion. So now we do a little algebra. So for example, the mass on both sides, my mass is going to, it's going to cancel out. One of the r's is going to cancel out, and we're basically left with this, that the velocity squared equals the gravitational constant times the mass of the Earth divided by the radius of the thing from the center of the Earth. Notice, and this is something I'll show on the next slide, notice that the mass of the thing that's orbiting doesn't matter. It doesn't matter whether it's me orbiting the Earth or whether it's some huge, somehow we've gotten a aircraft carrier into orbit. It doesn't matter. The mass of the thing doesn't matter because it cancels out. So we take the square root of both sides, and there you have it. So the velocity necessary for something to be in a perfect circular orbit around some spherical body, whether it's the Earth or Mars or anything, the velocity, now of course we're neglecting any kind of wind resistance or anything like that, although I assume that the kinds of satellites we're talking about are far enough up that maybe they don't encounter a lot of wind resistance. But the velocity for something to be in a perfect circular orbit is going to be the square root of the gravitational constant times the mass of the Earth, or whatever the mass of the thing, the spherical thing it's circling, divided by the radius, that is the distance from the center of the Earth or whatever spherical body you're talking about. So there you have it. That is the velocity that something in orbit needs to have in order to stay in a perfect circular orbit. There doesn't have to be any doesn't have to use any thrusters. There doesn't have to be any additional. You don't have to correct. It's just going to do it by the basic laws of nature. Okay, so some consequences of this formula, as I've already mentioned, that the motion of a satellite has nothing to do with its mass. It doesn't matter whether it's an aircraft carrier or little old me. The velocity is going to be the same regardless. Secondly, you're going to experience apparent weightlessness whenever Nothing but gravity is working on you. By the way, this is true if you jump out of a plane. As you're falling, you experience apparent weightlessness. And so anything that's circling the Earth in a perfect orbit or otherwise is going to experience apparent weightlessness. And the book mentions that an astronaut in a capsule is orbiting the Earth just like the capsule is. And so, again, you're going to experience apparent weightlessness in that sort of circumstance. Notice that the velocity of all satellites is going to be the same at a particular orbit distance. That's interesting. Of course, you can turn on thrusters and mess it up if you want, but in and of itself, gravity is going to take care of a circular orbit without any necessary firing of rockets and so forth. Okay, now there are some other little tidbits in this chapter, in this section of the chapter that we'll go ahead and finish out this video with. So, for example, what is going to be the time it takes for one orbital revolution at a particular radius from the Earth? Well, we know that in radians, see previous videos, the circumference of a circle around in radians is 2 pi r, where r is the radius. So if you know the radius from the center of the Earth, the distance in radians for the orbit of a satellite is going to be 2 pi times that radius. So we might say if velocity is distance divided by time, right? So the velocity of a satellite in orbit is going to be the distance, 2 pi r, divided by the time it takes to do one orbit. Okay, well, let's say we want to flip this around and find out what the time is. Well, I can find out what the time is by just switching the v and the t. So t equals 2 pi r divided by v. Now I'm getting somewhere because I've just derived a formula for v. So if I substitute the square root of the gravitational constant times the mass of the Earth divided by the radius, if I substitute that in the denominator for v, and again wave my hand and do a little algebra, then the time it takes for any thing in orbit to go once around is going to be 2 pi r to the 3/2 power. So I basically, you can leave it in the way it is in the second to last formula, but basically the square root of something is to the 1/2 power, right? So you have r to the 1 power in the top and r to the negative 1/2 power in the bottom, and so when you divide it through and subtract, you're going to have 1 minus a negative 1/2, which is 1 plus 1/2, which is 3/2. Anyway, that's where the 3/2 comes from. It's just algebra adding powers to the r. But anyway, and of course the r is in the denominator, there at the bottom. I might have said that a little wrongly, but anyway, the r is in the bottom of the bottom, so you flip it. It's just algebra. Don't worry. Pull the bag from the back of your plane seat and breathe gently into the bag. Anyway, then of course all you're left with is the square root of the gravitational constant times the mass of the Earth at the bottom. Just plug it into the calculator and it'll come out right. So that tells you to figure out what. So let's say someone says there is a cable satellite at such and such a miles from the Earth. Well, then you can find out how long it takes that satellite to go around the Earth one time. Okay, moving right along. Here's one that has to do with the total energy, the total mechanical or the total energy of anything rotating around the Earth. So total energy is going to be the kinetic energy plus the potential energy. Kinetic energy is 1/2 mv squared. Potential energy, we found out in the previous section, is negative gravitational constant times the mass of the Earth times mass divided by r. So I'm not going to do it all here. You can find it in the book. But again, you do a little mumbo jumbo, substituting in for v, squaring it, multiplying it all out, cleaning it up, crying a little, going to see an old friend to talk out the problems of algebra, and eventually you end up with negative g mass of the Earth mass divided by 2r. Notice that the total mechanical energy of any satellite is 1/2 the potential energy of the satellite. Okay, this has been Stuff in Orbit by Mr. Ken Schenk.